All right, everyone. How are we doing today? Doing all right. How was everybody's weekend? It was a weekend. Yeah. Lamenting yesterday that wish my weekend were a little bit longer. It never seems like there's quite enough time to get everything done that needs to get finished. But that's all right. So the plan for today is to continue on with the next chapter in our textbook, chapter 3. And just so everyone has an update, it is my intention to try to finish grading your exams through the end of the week. I have a little bit of grading that I have to catch up with in other classes first before I get to that. So I might have, I won't have grades uploaded before next class, but I will try to have them uploaded before we meet a week from today, unless some other crisis comes up or something. But that's the plan, so everyone knows what all that looks like. Okay. And in the meantime, we will continue on with what's going on with chapter 3. Just so you all know how the schedule kind of shakes out for the next bit of material is we're going to have another chapter test following chapter 3. Okay. So that's going to be between the exam that we've just taken and the next exam that we'll have over chapter 3. That'll kind of be our shortest period in between exams, because we transition into just pretty wildly different material for when we start talking about chapter 5. So that's the way that the schedule is put together. And then there will be a kind of a longer period of time between the second exam we take over chapter 3 and then the last chapter exam we take over those last 2 chapters. Okay. Also, so you know, we don't explicitly cover chapter 4 in here. There's some ideas from chapter 4 that we'll talk about, but for the most part, it's just kind of a rehash of a lot of the chapter 3 stuff with just more equations, okay, or more sophisticated differential equations involved. So I will mention the ideas that extend from that, but if you look at the actual scheduled sections that we're covering in the syllabus, chapter 4 is not on there, and that's why I wanted to explain. Okay. So this section here is titled Homogeneous Equations with Constant Coefficients. All right. So there are 2 important words there, okay? Homogeneous, or 2 important conditions. Homogeneous and constant coefficients. So where we're going to start is by noting that we're having this discussion about specifically second order differential equations. Okay. So in our previous work up through all the material included in our exam that we've just taken, we have been dealing with only first order differential equations, okay? Now we're going to be dealing with second order differential equations. And there are a couple different ways that we can write this down. One's a little bit shorter than the other one, but they both mean the same thing, okay? So we need to make sure that we understand both forms of the notation. All right. If we want to talk about a linear second-order differential equation, it has to be the case that the differential equation is expressible in this form. The last one is G, yes. So P, Q, and G. In this notation here, okay, we remember from last chapter that our linear differential equations needed to be, or our linear first order equations need to be expressible in this format. Okay, and sometimes there's a function coefficient on the highest order derivative term, and we have to divide by that function and then relabel things in order to get to look like this, but that is what a linear first order equation looks like, or may be written as. It is linear if and only if it can be transformed into this. Likewise, second order equations are linear if and only if they can be written like this. And you see how the pattern matches up with what we had previously, right? We have the highest order derivative term with no function coefficient, or the function coefficient is 1, however you want to think about it. And then everything else is all of the lower order y terms multiplied by exactly a function that depends only upon the independent variable. Okay? You can't have y prime squared or y times y prime or sine of y, anything like that. Anything like that makes the equation nonlinear. Okay? But once we have this form, we can say that this is a linear second order equation and go from there. Now, the title of our section had a couple of qualifications that we wanted to discuss for our differential equation. We wanted them to be homogeneous, and we want them to have constant coefficients. Okay? So that means two things. A homogeneous equation is one in which this is 0. All right? That makes this a homogeneous a homogeneous linear second order equation. And I'll just write ODE as a shorthand for ordinary differential equation. Okay? Homogeneous equations are nice because we will find out as we progress through the chapter here that this function g represents, in general, something called a forcing function. Okay? In the problems that we're going to be studying primarily throughout this chapter, we're going to be concerned with oscillatory motion. And that oscillatory motion is going to be motion that occurs based upon what's going on with the initial value for our system. Okay? And if we have some non-zero function on the right-hand side of the differential equation, that is going to interfere with the natural behavior of our system that's being just our physical system that's being modeled by the differential equation. Okay, it's going to add energy to the system somehow. All right, and it makes the problem harder to solve. Okay, so we're going to start by not worrying about the right-hand side. We're going to develop our theory for how to solve homogeneous problems, and then we are going to figure out how to adapt those solutions to deal with the cases that are non-homogeneous. Non-homogeneous systems, of course, being the ones that have a non-always equal to zero function g. Okay? And just to be clear, when it comes to the idea of a forcing function, it can be zero sometimes. All right, that doesn't make the equation homogeneous. An equation is homogeneous when the right-hand side is exactly the constant zero function. Does that make sense? So when we say the right-hand side is zero, we mean the right-hand side is the zero function, not the right-hand side's function assumes the value of zero sometimes. Okay, it's always zero. Or at least if we're being very, very pedantic, zero almost everywhere, which is something you don't need to worry about unless someone has told you that you need to take a class called real analysis someday down the road, which is graduate school stuff. Anyway, so there's the homogeneous part, and then constant coefficients. You can probably guess what that means. It means that our functions for for P and Q are going to be constants. They're going to be numbers, right? They're not going to have T dependence. And just to not waste time, I will write it the way that we tend to write this in practice, which is put the number A in front of y double prime, and then by prime plus cy. If A is non-zero, we see that without loss of generality, we can very easily make this look like the standard form for a second order equation, right? Okay, and if A is equal to zero, it's not a second order differential equation because 0 times y double prime would annihilate that term and I wouldn't have a second derivative that appears in my problem, right? So this, of course, is under the condition that A not be 0. Okay, so now this, what I have written down, is a homogeneous linear second order equation with constant coefficients. Okay, so this thing that we have written down here finally has all the vocabulary terms. Now, compared to some of the other differential equations that we've looked at, other than the fact that this is second order, and maybe we're not 100% sure how bad that's going to make things, it looks pretty easy, right? I mean, it looks less complicated than some of the other things that we've written down, right? I'm sure you, like, at first blush, for instance, exact equations look a lot worse than this. Okay? And it turns out that I'm not leading you astray here. Okay? It's actually not that difficult to solve this problem. Okay? Or problems that look like this. They all face or follow a pretty basic convention. So let's start off with an example here. All right. We're going to say y double prime and minus y equals 0. And we are also going to give ourselves initial conditions here. We'll write it like this. Okay. So that you are aware, okay, when we prescribe initial values for second order differential equations, or for any problems in general, it is the case that we tend to need, or we're going, in order to be able to solve the initial value problem, we need as many initial conditions as we have derivatives. Okay. In the first order differential equations that we've dealt with previously, we had one initial condition because there was one, the highest order derivative was 1. Here we have 2 derivatives that show up in the differential equation, so it is necessary for us to have 2 initial conditions. All right, one for each of the lower order derivatives. Okay, now we've used the why not notation before as a way to signify the value of y when t is equal to 0, right? That notation is familiar to us, okay? A way to adapt that when we start having to prescribe initial conditions for the derivative is to put a prime over the y0, so that means y prime evaluated at t equals 0. Okay? But in some places, I will not tend to use the notation this way, but if you happen to look at other resources or other textbooks, you should know that this happens sometimes. What they will do is they will use the 1 in the subscript to mean the initial condition for y for the first derivative. Okay, like you would use that subscript for taking the first derivative in a partial derivative sense for Calc 3. Okay, sometimes it's just the way that people write it sometimes. Okay, I'm probably going to stick to using this version of the notation or just writing the full term like this to avoid ambiguity. But you should know that that happens elsewhere. Okay, now what we want to do is look at this example in the context of the information that we have available to us already, right? We look at our form that we have from up here and compare it to the what's going on with our differential equation. And we notice about this that a is equal to 1, b is equal to 0, and c is equal to -1 for this thing right here. Okay? Now, what we want to do is try to figure out the answer to the question that is posed by this differential equation. And what I can do is I can add y to both sides. And now we have the question, what function is equal to its own second derivative? Okay. It has been suggested here that one candidate for the solution is the exponential function. Okay. Is this the only function that's equal to its own second derivative? Not sine, but isn't hyperbolic sine equal to its own second derivative? This was in Calc 2. You're supposed to know this.
Yeah, my Calc 2 was 3 years ago.
Okay, all right. Well, I have bad news because we're gonna have to remember everything from Calc 2. Okay, well, it turns out the answer is yes. I'm being coy here because someone kind of was close to putting their finger on it, so I went ahead and let you all know. And then in the chat they have the other function, which is probably the more obvious one that we are looking for, which is e to the negative t. Because if you take two derivatives of this, you get negative 1 squared, which gives you back e to the minus t. Okay, so good job on that. All right, so I'll call these y1 and y2 as our solution set. And while this one's not wrong, we're not going to worry about it for right now. Okay, but the fact that there are several answers here is something we're going to have to deal with, right? We need to make sure that we are accommodating for all of these things properly. All right, now we know, because since I've already kind of let the cat out of the bag here, that there are other functions, but are e to the t and e to the minus t it? What else can I do? Is this equal to its own second derivative? It is, right? Because the derivative of a constant times a function is just a constant times the derivative of that function. And I can certainly take two derivatives, can't I? So it doesn't even actually matter what that number is, does it? It could be any real number, right? And I would still get the fact that it was equal to its own second derivative. So what this is really saying here is that my solutions would look like any real number times something that's equal to its own second derivative, right? Now, what happens if I add these two things together? Is that equal to its own second derivative?
Yes, because it's the second derivative.
Yes. You have to take two derivatives, that's correct. But if you take two derivatives, you get the same function back, right? Because we know that the derivative is a linear operator, right? The derivative of a sum is the sum of derivatives. And didn't we go really far out of our way to make sure that this differential equation was linear? And the property of linearity says that the linear operator applied to a sum is the sum of the linear operator applied to the objects. And the linear operator applied to a constant multiple of the subject is equal to the constant times the linear operator of that subject. So what I'm saying is that L of x plus y is equal to L of x plus L of y, and L of alpha x is equal to alpha L of x. That's not the first time I've written that down. Okay? So when I say linear, you have to remember that this is the kind of thing that I'm referring to. Okay? We don't use the word linear unless this matters somehow. Okay? That's the whole point of making sure that we can say that this differential equation is linear, so that it has that property. The differential equation applied to a sum of functions is equal to the sum of the differential equation applied to each function individually. And a constant times the function is equal to a constant times the ODE applied to the function. It has that linearity property. If I don't have a linear ODE, this doesn't work. Okay? Now, the reason this all matters is because, in general, my solutions are going to look something like this, right? And I can, in fact, write a general solution to my differential equation in this form. This is what we call a general solution. Okay, general solution of the homogeneous equation. Is anyone with us taking linear algebra? Okay, the handful of people here live say no. I'll give the people on the internet a second to respond. Even if you haven't, just say no, just so I know people are hanging out here. All right, got a couple no's from the chat, one yes so far. All right, now for my one linear algebra student, you should recognize that this is a linear combination. Okay, it is a linear combination of the two different functions that we have found that comprise solutions for the differential equation. If you have a constant times an object plus some other constant times a different object, and you can do this as many times as you want, have as many constants times a thing, add it all together as you like, okay? This is called a linear combination. And it is one of the most important objects in linear algebra. Okay? Yeah. So this part would be the K and the C and what I've drawn down below. And this part would be the X and this part would be the Y. I wrote underlined letters because I'm trying to evoke the way that we would write it down in the context of linear algebra. No. Sorry, that's just sloppy handwriting on my part. That's a 1. Okay, so the idea here is that we have two different functions, y1 and y2, and two different constants, c1 and c2. And if I take a constant times a function plus a constant times another function, that forms a linear combination of solutions to the differential equation. And because our differential equation is linear, a linear combination of solutions is a solution. Does that make sense? So I have y double prime minus y equals 0 as my differential equation, right? And we're saying that y1 is equal to e to the t, and y2 is equal to e to the minus t. Okay? I am proposing that we take a linear combination of these two solutions and plug into our differential equation. Okay? Now, what I'm going to do is I'm going to write it out without using our functions explicitly, just doing algebra. And then when we get to the part that would require the substitution, show that, yeah, this just works. Okay? So we have C1, C2, Y2, T. And I'm going to use prime notation for the derivatives just to make life easier. So it looks like this, right? Now, as we've discussed, the derivative of a sum is a sum of derivatives. I can take the derivative twice here pretty easily. Okay, we know that the constants don't affect it. So I get right away that this is C1 times Y1 double prime T plus C2 Y2 double prime T minus C1 Y1 T minus C2 Y2 T equals 0. Right? I can rearrange this equation. To put it into this form. Okay? I arranged the addition and factored out the C1 and the C2. Now, these are solutions to the differential equation, right? Each of them are individually. Doesn't that mean that this and this have to be 0? That's y double prime minus y. Because y1 and y2 are supposed to both solve that. Yeah? Okay. Sure looks an awful lot to me like 0 plus 0 equals 0. So what we have shown is that for this differential equation, A linear combination of solutions is a solution. And it wouldn't have been much extra work to show that this actually holds for any linear differential equation, right? You have some more work to do in managing the derivatives, but a linear combinations of solutions is a solution. And that fact is going to be extremely important for us moving forward in the material here, okay? All of our solutions for this entire chapter are going to be structured as these linear combinations, because we are going to find out that that in order for us to be able to solve an initial value problem for a second order equation, in order to make sure that we have a wide enough reaching family of solutions, is what we're going to call them, we have to have a linear combination involving two linearly independent functions. I need two functions that are different enough that they cover the solution space. All right? And then once they cover the solution space, what I can do is I can use the initial values to figure out what the constants in front need to be in order to satisfy the initial condition for the problem. Okay? So the C1 and C2 values are going to be determined like they were for first order equations by our initial condition. That's how we're going to find the constant integration. Okay, so where we are now is that we have shown that this is a solution to that differential equation. I didn't explicitly write the e to the t and the e minus t on the previous screen, but we talked through why those are both solutions, okay? And we showed a linear combination of them is also a solution to the differential equation. What we want to do now is apply our initial condition, and I need to remember if that's a 2 or a minus 2. Yeah, it's positive 2. Okay. All right. So this is now what we want to do. Okay. When y is equal to 0, we know that the function has to be equal to 1. And so we plug in 0 for our differential equation. And we end up with the equation that C1 plus C2 must equal 1. Because e to the 0 is 1. All right. Now I have two unknowns in one equation, but I have another initial condition that I haven't applied yet, right? So we know that the first derivative evaluated at 0 has to be 2. And so what we need to do is evaluate our function after taking its derivative at 0. So differentiate first and then plug in 0. And that gives us our second equation. So we have a system of two equations and two unknowns. And this isn't even calculus. This is algebra. Okay, we know how to do this. Add the two equations together by the elimination method. We get 2c1 is equal to 3. So c1 equals 3 halves. And now that I have the first value, I can plug that into one of the equations and see that c2 has to be equal to negative 1/2. And so the solution to our initial value problem is 3 halves e to the t minus 1/2 e to the negative t. All right. And so what we would do at this point, in order to verify that everything is correct, is plug in our initial values and make sure that everything works out the way that it's supposed to, right? So if we plug in t equals 0, we get 3 halves minus 1/2, which is 1. Okay. And then you take the derivative of everything, plug in 0, and we would get 2, right? So we have solved the initial value problem and got everything put together here. Okay. Now, I know that took us a long time to talk through, all right? But we talked through already about half of the theory for the section, okay? There's one other theory thing that we'll need to talk about, which is handling the solution space problem that I had mentioned earlier. But that's not for right now. What I want to talk about otherwise is the pretty simple general approach that we use to solve these kinds of problems. Okay, this is what our equations look like, right? Homogeneous second order equations with constant coefficients. All right. Now, one of the things that we had previously from our other exercise that we just did was the fact that both of our solutions look like this. E to the power of some number r times t, right? In the previous example, it was r equals 1 and r equals minus 1. Okay, but there's some number up there, right? So what happens if I make the educated guess that my solution y is going to have the form e to the rt for some constant r, and plug that into the differential equation to see maybe what the condition on r has to be in order to get this to work? So we replace y with r everywhere, and we have some calculus to do. If I take the derivative of e to the rt twice, I just get 2 factors of r out front, right? And then e to the rt. And if I take the derivative once, I get 1 factor of r. And if I take the derivative no times, I get no factors of r. Now we see that e to the rt here is in each of these terms. And it makes sense for us to factor that out. Now, What do we know about e to the RT as a function? Or perhaps another way to get to the answer, is if we look at the expression that we have written down right now, that equation, how would we normally solve that equation? No. If I have a product in my exponents, the identity for that is this. They have to be added to become a product. Does that make sense? Okay. So we can't do that. But if we look at this expression here, okay, this is an algebra question. How do I solve this equation? We set the factors each equal to 0, right? Using the principle of zero product. So we should have AR squared plus BR plus C equals 0 and e to the RT equals 0. When is e to the RT equal to 0? When is the exponential function equal to 0? Or if it's the negative exponential function? Is it ever equal to 0? Or is it strictly positive? It's strictly positive, right? This equation's nonsense. It never happens. Okay? Which is good for us because that means we only have to worry about this one. Okay? All right. I know it's late in the afternoon, early evening, whatever. Okay? In a couple of sections, we are going to be doing some of the hardest stuff from Calculus 2. Okay? Some of the integrals that you all hated doing, all right, are coming for you in sections 3.5 and 3.6. All right? This whole pretending that we don't remember algebra or not thinking very hard because you're waiting for me to give you the answer is not going to work. All right? Engage. All right? Because if you wait to engage until it actually gets challenging, it's going to be too late. All right? And I'm telling you this now because no kidding, we're going to be doing partial fractions, trig substitution integrals type stuff by the end of next week. All right? So, lock in. Okay, so because this factor here is never equal to 0, we can focus on this part here. And for this part, we are going to give this a name. We're going to call it the characteristic equation. All right, and the characteristic equation's job is to tell us what is the condition on R that is going to allow us to be able to determine the solution of the differential equation. Okay, because the e to the RT here is never 0, so it doesn't impact whether or not something is a solution of the differential equation. Okay, it's all controlled by the characteristic equation. But the characteristic equation will tell us which values of R make this true. And what do we use to solve this problem? The quadratic formula, right? It is a quadratic equation, so we use the quadratic formula to solve it. Okay? Or if it's when we have actual numbers plugged in there, maybe we can factor it and then just do factoring because that'll be faster than plugging everything into the quadratic formula. But that's it. Okay? That's the first 4 sections of this chapter. Is do you remember the quadratic formula? Okay? And then there are some things that we have to remember that are consequences of it as we plug things into differential equations, but the techniques that we're going to be using to begin with are just that. Use the quadratic formula or some other thing that allows you to solve a quadratic equation. Okay? So we find the roots of the quadratic, and then once we have the roots of the quadratic, our solution is going to look like in general this. Okay? Now, there are a couple of caveats. All right. We need to make sure that the functions involved here have a special property, namely linear independence. If the 2 roots for our equation are the same, then that gets messed up. And of course, we know that if we're solving quadratic equations, that we can have solutions to the quadratic equation that are complex valued, right? And we're not going to shy away from that in this class, okay? So if we have complex valued roots to our characteristic equation, there are functions that are real valued that represent the solutions in that case. And they turn out to have some important applications, in particular having to do with oscillatory motion and electrical current, okay, which is our applications that we're going to see at the end of chapter 3. Okay, we're going to talk about oscillatory motion and spend some time working through the vocabulary for that, as well as RLC circuits, if you're familiar with that. Okay, some of you, has anyone taken circuits 2 or something? Okay, we're gonna solve those problems for real instead of dancing around the calculus. We're gonna actually do the calculus to describe the charge as a function of time in the system. Okay. All right. Okay, yeah, I'll do that now. Sorry, I'm organizing my thoughts here. All right. Just so everyone knows, before we move on to the next part of what we're going to be talking about today, in the online notes, which there's a link to the table of contents for all of these available in Blackboard, section 3.2 goes through in the online notes and fills in a lot of what the book skips over in terms of the background material that's related to kind of the linear algebra connection to what it is we're talking about in this class. Okay. I only have a finite amount of time to talk about these things here live with you all, but one of the really frustrating things about the textbook, at least from my perspective as someone who's trying to convey as much information as possible and give a holistic picture of how these things go, the textbook does a really bad job, or at least I think a disservice to you all as students, by dancing around the stuff that comes from Calc 3 and the stuff that comes from linear algebra that we need to utilize in certain parts of this class. And there's kind of a crash course in linearity and vector spaces, kind of focused in on how it applies to differential equations, a couple of the ideas that we've talked about today, but also written up in more detail on the 3.2 page here, okay? And then later on, we get into some of the material that I want to make sure that we bring up in regards to something called the Wronskian, which is an important theoretical tool for us that we need in order to evaluate what's going on with the solution candidates to our family of solutions. Okay. All right. Where do I want to start? Okay. All right. There's something called the Wronskian that we need to make sure that we understand. Okay. And typically the way that the Wronskian is written is like this. Sometimes people will use square brackets instead of two sets of parentheses. It doesn't matter the way that you write it. I'll probably use the square brackets most of the time, but we can write it like this. And the idea behind this is that it is a special type of determinant. Okay, so the idea here is that I have a couple of solutions, y1 and y2, that I want to represent as a linear combination to serve as a general solution for my differential equation. And what I'm looking for is a mechanism to determine that in the space of continuous functions continuously differentiable functions, that y1 and y2 are different enough to cover the entire solution space. All right? I need them to not be linearly dependent. If we're talking about them in terms of lines in space, I need them to be not parallel or not collinear, right? I can't have the two lines be on top of each other. I need vectors that point in different directions so that I can go anywhere in 2D space here, right? If one of those is missing, I can only go in this direction. I can't get to every point in space, which means I can't satisfy every possible initial condition, right? If I can move in this direction and this direction, then I can always get to the point, right? By choosing the right amount to travel in both directions. Okay? That's the very short version of what linear independence means. Okay? But since we're talking about functions, we have to be able to deal with that in the context of functions. It turns out that this formula here, this Wronskian, will tell us if the functions y1 and y2 are different enough in order to cover the solution space as solution candidates for a second order differential equation. So what we do is we take the determinant of a 2 by 2 matrix and we want it to not be 0. The reasoning for that is, and my linear algebra students will be familiar with this, this matrix is non-singular if and only if its determinant is non-zero. Okay? The singularity of a matrix is connected to whether or not its columns are linearly independent. Okay? So if this determinant here is non-zero, it means that those columns are linearly independent vectors in the function space. Okay, which I know is a lot of fancy vocabulary, but basically this is the mechanism that we use to check to see if our solution sets are different enough to work. Okay? So let's do one that we have seen before. What about the Wronskian between e to the t and e to the minus t? We write e to the t, we write its derivative, we write e to the minus t, and we write its derivative. We get e to the t times minus e to the negative t minus e to the negative t times e to the t. And that's non-zero. E to the negative t times e to the t, of course, is e to the 0, which is 1. Okay? So what this tells me is that e to the t and negative e to the, e to the t and e to the minus t are linearly independent. Because they satisfy this condition. And a question we could ask is what happens if we look at e to the t and the hyperbolic sine of t? Are those functions linearly independent? Could I describe the solution to my example earlier using these functions instead of e to the t and e to the minus t like we did, right? The derivative of hyperbolic sine is hyperbolic cosine. That probably does nobody a lick of good, right? But maybe if we remember our identities for hyperbolic sine and hyperbolic cosine, that we could figure this out. Right? So now it's a matter of going through and computing the determinant here. There's going to be more simplification involved, but I'll let you all work that out for yourselves. Okay? What you should find is that you get a non-zero answer. Okay? And the fact that the answer is non-zero should be not surprising because the sign hyperbolic has the e to the minus t that we had in the previous answer, right? It adds that in. So even though it's a little bit dependent upon e to the t, it's not wholly dependent upon it, right? Okay. Now, a variation of this may or may not be a quiz question, which is why I'm not doing the rest of it. Okay, but that's the idea. So let's talk through where we have gotten today. Okay. It is my, of course, strong recommendation that you take a look at the online notes for 3.2 in particular, okay? Because the beginning part, which I've scrolled partially through already, shows the backup linear algebra material that I hinted at throughout today's lecture. And then also here, kind of at the midpoint of the discussion, talks about the Wronskian and then does some examples involving Wronskian computations for you to follow along with, okay? And then again, ties it back to linear algebra, talking about the idea of linearity and how it connects to vector spaces. Because ultimately what we're doing is we are talking about the vector space of functions, okay, that have enough derivatives to potentially solve the differential equation, and then move on from there. Okay, now all of this material is not in your textbook. All right, it skips all explicit references except when absolutely necessary to linear algebra. Okay, if you are interested in taking linear algebra eventually, it is useful to read through this because it will give you some context for some of the things that will come in about midway through linear algebra. All right. When linear algebra starts, you're just talking about matrix arithmetic and how to multiply things and maybe a little bit about what the columns of a matrix mean and how to do row operations. And then when you get to chapter 3 in differential equation or linear algebra, excuse me, you start talking about vector spaces. Okay? And you talk about vector spaces in kind of an abstract sense. This information here is useful because it is an application of vector spaces. And probably not one that you're going to see a lot of in your linear algebra class due to the fact that there is a tendency to stick to the more geometric examples, the ones where you can draw arrows and stuff for, because it's easier to intuit those. But this is just as important, and I don't want to gloss over the fact that what we're really talking about and what this Wronskian thing really is an idea that comes to us from linear algebra. It gives us a way to examine elements of a function space and be able to determine if these things are linearly independent or not. Okay? All right. And then the rest of it, just working through examples, a little bit about operator notation. And the other thing that I want to mention, and I don't have time to do an example of it right now, but I will use this technique next class. So you can read through this if you want to preview it a little bit. Okay. This is another thing from linear algebra. It's called Cramer's rule. And Cramer's rule is a neat way to write down how to solve systems of linear equations. Okay. So this right here is a system of linear equations, and it's the type of system of linear equations that pops up when we need to figure out what our constants are after applying the initial conditions. Okay, we had something look very similar to this earlier for us, right? there's a way to solve this using what's called Cramer's rule. What you do is you think about this equation in matrix form, and then you use this determinant formula, which is the determinant of A with one of its columns replaced by the right-hand side of the equation. And I use colors here to indicate where the replacements occur. And it's divided by the determinant of the original matrix A. And this gives you a direct way to compute the values of C1 and C2. Okay, so if you want to practice this, take a look at this formula, compare it to the example that we did in class today, and you should be able to reproduce 3/2 and -1/2 using this Cramer's rule formula. Okay, this is another thing that's not brought up in the textbook, and I'm bringing it up now in particular because it is a very useful way to not have to use a very complicated formula that comes from your textbook in one of our more difficult sections for this chapter 3.6. Okay, there's something that we can do where we just think about it as Cramer's rule instead of using the nasty integral formula that shows up in the textbook, because they don't talk about this version of it. All right, so we'll be using Cramer's rule to practice to build up to that, and then we'll use Cramer's rule with functions instead of Cramer's rule with numbers at some point in order to cut down on having to remember an irritating formula. Okay, so that's what we'll be doing for the next couple weeks. Enjoy your evening, everybody, and I will see you next time.